Okay, so let's start the session. We have an exciting session on quantum cryptography. The first talk is by Kwak Yu on how to achieve public key encryption from one-way functions using quantum resources.
Thank you for the introduction. So hello, everyone. Today I'm going to be talking about our paper public key encryption with quantum keys. And this is joint work with Prabhanjan, Alex, Luis, Julio, and Michael. So let me start with some motivation questions. So we saw this picture on, I think, in the first day of the conference. So this is the two cryptographic ones in the Imperials of 5 ones. So we have mini crypt where we have one-way function, and cryptomania where we can do all the amazing public key cryptography. And there's some black box separation between the two ones. And this picture changed dramatically when we consider quantum computation and quantum communication. In particular, two works, the first one by Grillo and they show that using quantum computation and quantum communication, you can do several cryptomania primitives using only one-way function. And then people start asking the question, can we even go lower? So for that, let me recall the notion of a random state generator, which you already saw yesterday in the invite talk. So basically, PRS, or pseudo-random state generator, is a quantum algorithm that take input a classical string X and output a quantum state psi X. That is computationally indistinguishable from a hard random state. And in 2021, Fresno showed that one-way function cannot be constructed from PRS in a black box way related to some quantum oracle. So that shows there's also some separation between one-way function and PRS. And for the application, it's more useful to consider an variant of PRS, which is pseudo-random functionalized state, introduced in 2021 by Ananth Q and Yuan. So PRFS, now the algorithm G also has some secret key K, and the output depends on both the classical string X and the secret key K. So using the notion of pseudo-random state, random state generator and its variance, a series works so that you can do a lot of crypto even without one-way function. So the name of this one is we call it micro Q crypt. I think it's suggested by Murime. And so if you see on the picture, so again, there's some black box separation between micro Q crypt and mini Q crypt. And if you see on the picture, then there's one remaining object in cryptomania has not been addressed before, which is public key encryption. And so in this work, we ask the question where to put the quantum public key encryption. So in this work, we initiate the formal study of quantum public key encryption, or QPKE. So we define, we give the definition and security notion for QPKE with different flavors. And then we give several constructions for QPKE with quantum public keys from one-way function or even from weaker assumptions. And then we also answer the question whether we can achieve unconditional security for QPKE, because in the quantum setting, the close related notion, which is to public key encryption, which is a key exchange. We know that we can achieve key exchange unconditionally by the famous protocol QKD protocol. So in this work, we saw that it's also impossible to achieve unconditional security for QPKE using shadow tomography techniques. And we also want to point out that there's another proof using quantum Sanubal pointed out by Takashi Zamakawa, but that proof is more less direct and is used more new quantum cryptographic primitives. So let me go to the first part of the talk, which is the definition. So QPKE, the definition QPKE is kind of straightforward. It's just the same as classical public key encryption. We have the key generation, we have the encryption and decryption. So few differences. The first one, for the encryption, the ciphertext can be either classical or quantum state. And for the key generation, the first thing that the secret key is a classical string, just like in classical public key encryption. But the public key can be either classical or a quantum state. And in our work, if we only consider for the case where the public key is quantum state, we require it to be a pure state. And when I will explain the reason that why we consider this notion later. So for the security, we just follow the standard semantic security paradigm, where basically the other three cannot distinguish the encryption 0 and 1, except that the other three now also given a polynomial many copy of the public key. So the reason is that because in 0, we expect the public key to be unclonable if it's a quantum state. So that to make the security notion to be meaningful, we allow the other state to obtain polynomial many copies of the same public key. And also if the public key is pure state, then this implies a non-trivial way to distribute the quantum public keys. So that's actually suggested by Gosteman in 2005. So the idea is we can use swap tests to compare the public key with different certificate authorities. However, we know that this approach only achieve inverse Pauli soundness, and I will be talk more about that at the end of the talk. So let me give you a quick glimpse of our construction from one-way function and from PIFS. So for the full, so those are the really simplified version of the constructions that we give in the paper. So for the first one, from the one-way function, for the key generation is simply the secret key just simply an PIF key, and the public key is uniform superposition of own evaluation of the PIF under the SK. And for the encryption, the first step we just measure the public key in the computational basis to get a pair classical strings X and Y. Y is the image of X under the secret key. And the idea is now we can use Y as the secret key for some symmetric key encryption that we can build from one-way function. And X is a hint that if we have the secret key, we can recover the secret the value Y. And the decryption is quite straightforward. As I said, you know the secret key SK, you can recompute Y from X, and then with Y you can decrypt. So the intuition for the security proves that if you don't have the secret key SK, then basically you can make Y to be uniformly random string. And if Y is a uniformly random string, then we can reduce the security of this scheme to the security of underlying symmetric encryption. And the construction from PIS, that the one that I present here, follow the same method. So for the key generation, you also the secret key for the PIS, and the public key again is just a uniform solution of the PIS. And the encryption now, instead of measuring the whole public key, we only measure the first register, the X register, to get a classical string X. And after the measurement, the public key just collapses to the side K SKX. And for the encrypt, to encrypt 0, we just return this pair of X and psi SKX. Otherwise, we return X and then maximally mixed state. And for the decryption, we using some useful property of PIFS. You can verify if the quantum state that you receive from the ciphertext is indeed psi SKX or not. And from that, you can do the decryption. And again, the security proof for this construction also follows the same approach that I just present for the one from one-way function. So that is the two construction that simple construction. And in the paper, we also give more involved construction achieving CCA security or construction from more assumptions than just PIFS in one-way function. So for the last part of the talk, I will present a quick proof for the impossibility reason. So the main observation is that for, let's say you have PK0, which is the honestly generated public key, then the observation is that for any other blue PK, if PK0 and PK blue they are close enough, then you can use the corresponding secret key of PK blue to decrypt any ciphertext that encrypted with PK yellow. So that is so here's the formula for the statement. And then the next step, we only need to basically we need to estimate on the distance of PK yellow and the distance for all possible PK blue with PK yellow. But here's the crucial point that we only given polynomial many copy of PK yellow, and that prevent you from the trivial brute force. And the technique we use is to use shadow tomography to estimate this value and find the appropriate SK that can use to decrypt this ciphertext and break the security. So to conclude, in this talk, we present the definition of quantum public key encryption. We show several impossibility and possibility for constructing QPKE. And we know that there's some caveat. So first, our construction will be broken if the others can modify the quantum public key before the encryption. And a single copy of the public key can be used only by one encryptor. So there are two open questions. The first one is how we can distribute quantum public keys to achieve negligible soundness, for example. So this have been partially shown in follow-up works. And I think the more interesting question is to study the possibility or impossibility of reusable QPKE, where one public key can be used by many encryptors, just like in the classical public encryption. And for that, I conclude my talk, and thanks for your attention.
Questions?
In your construction of the PKE, if you can show the slide, this involves like this one. This involves summation over the domain of the PRF, and classically it would be very expensive. Do you have an efficient way of creating such a state?
So you can easily compute the PK. First, you put uniform superposition on X that you can just do by applying Hadamard on zero state, and then you evaluate the PF coherently in superposition, and that you would give you this. That's the answer.
Thank you.
Any other questions? I have a question. So you talked about reusability of your construction, right? Don't you already get reusability? Once you measure, you get XY. Can't you use XY to encrypt many ciphertexts?
So basically, you can in the construction that we give in the paper, you can reuse X and Y to do many encryption, but like X and Y has to be kept secret.
Oh, I see. Okay, so there are no more questions. Let's thank the speaker again.
Thank you.
Okay, so the next talk is one out of many unclonable cryptography by Fuyuki Kitagawa and Ryo Nishimaki, and Ryo will give the talk.
Thank you for the introduction. So I'm going to talk about one out of many unclonable cryptography. This is a joint work with Fuyuki. So this is a short summary of our work. We propose new definitions for unclonable cryptography. This is a relaxed variant of indistinguishability-based unclonability. And we also propose construction of unclonable secret key encryption in the standard model under this relaxed definition. We also propose unclonable predicate encryption and copy protection for single bit output point functions. And we also propose single decryptor encryption in the standard model. This is under the standard definition. Okay, so let's see what is unclonable cryptography. In this talk, we propose, in this talk, I focus on unclonable encryption. So first of all, it is easy to copy classical information. So say Alice want to store her encrypted file on the cloud server. And after that, Alice, when Alice download the encrypted file, the cloud server may keep a copy of the encrypted file. So it is impossible to prevent copying digital information by using classical cryptography. However, if we use power of quantum computation, we may be able to prevent copying quantum information due to the no cloning theorem. So Broadbent and Rod introduced the notion of unclonable encryption where ciphertexts are quantum state and copy protected. The syntax of unclonable encryption is the same as standard encryption. This is a security game of unclonable encryption. First, the adversary sends two plaintext to the challenger, and the challenger encrypt, flip a coin and send a challenge ciphertext to the adversary. And then adversary 0 generate quantum state over two registers and send the first and second registers to adversary 1 and 2 respectively. These two adversaries cannot communicate each other. After that, the challenger sends the decryption key to these two adversaries. And then they output a guess for the challenge ciphertext. If the probability that these two guesses are correct is less than half plus negligible, then we say that this is unclonable unclonable indistinguishability. So let's briefly see the previous works. Broadbent and Rod presented the first unclonable encryption scheme that satisfies one unclonable one-way secure unclonable one-wayness in the standard model. And Ananth Karaoglu improved their scheme. And later, Ananth Karaoglu, Lee, Liu, and Chandri presented the first unclonable encryption that satisfies unclonable indistinguishability in the quantum random oracle model. And Ananth Karaoglu, Liu also improved their scheme. So the big question in this area is, can we achieve indistinguishable secure unclonable encryption in the standard model? In this work, we construct unclonable encryption in this, unclonable indistinguishable secure unclonable encryption in the standard model, but under the relaxed definition. We construct this scheme from the standard assumptions, LW assumption. Okay, so let's move to the new definition called one out of many unclonability. So the first part of this game is the same as the standard unclonable indistinguishability. But adversary 0 now generate a quantum state over any registers and send each state to each adversary of the next stage. And the challenger now randomly choose alpha from 1 to n, and send the decryption key only to adversary alpha, not all adversaries, only alpha. And this adversary alpha output a guess B star. And if the probability that the guess is correct is less than half plus 1 over 2n plus negligible, then we say that this is one out of many unclonable indistinguishability, satisfy unclonable indistinguishability. We can derive this trivial band as follows. So if the adversary 0 passes the challenge ciphertext to say adversary 1 as it is, then adversary 1 can win this game with probability 1. Yeah, the other adversaries can output a correct guess with probability half. So we can derive this trivial winning probability. And this security means the following. So the adversary cannot generate n copies with probability 1 over n plus delta. Why? So if the adversary can do this, then the adversary can win this game with if adversary succeed in generating n copies, then the adversary can win this game with probability 1. And if the adversary do not succeed, still they can output a correct guess with probability half. So we can derive this this bound. But this probability is probability contradict to the security of one out of many unclonability. So the adversary cannot succeed in generating n copies with probability 1 over n plus inverse polynomial. And I briefly explained the interpretation of new definition. This definition roughly says that the expected number of successful copied quantum object is almost equal to 1. Why? Let's see this for n equal to 2 case. So suppose that we check we consider slightly different again, but this is equivalent to the definition what I explained in the previous slide. Let's assume that we check adversaries. Oh, sorry, both adversary A1 and A2 output guesses, and we check only one answer. And then the success probability, we can interpret the success probability like this. So here, P sub CC is the probability that both answers are correct. And P sub IC means that A1 is incorrect and it is correct. P sub CI is the inverse of P sub IC. Okay. So we check only one answers of these two adversaries. So we can write the security success probability like this. And so, by the way, the standard unclonable indistinguishability says that the expectation of P sub CC is less than half plus negligible. And we can rewrite this inequality by multiplying 2. We can obtain this inequality. The left-hand side means that the expected number of correct answer. So we can say that the expected number of correct answer is less than 1 plus half plus negligible. We can easily generalize this to general case n case. So this said that the expected number of correct answer is less than 1 plus 1 over n plus negligible. So if n is large, this is almost equal to 1. And so there are a few related works. Behera Satas proposed a similar security definition for quantum money with a similar security flavor of this notion. And Alonso also proposed the definition for copy protected program by focusing on expected number of successful copies. Now, let's move to how to achieve our one out of many unclonable encryption. So first, we can show that one out of many unclonable encryption is equivalent to one out of many single decryptor encryption, which is a copy protected version of public key encryption. We can prove this equivalence by similarly to the result by Georgia and Chandri. Note that here, GZ20's SDE is different from CLLZ21's SDE. And next, we can show that one-time strong anti-piracy SDE implies one out of many SDE. The technical core of this result is the next part. We can show that a single key and succinct key ciphertext policy functional encryption implies one-time strong anti-piracy single decryptor encryption. Interestingly, we use watermarking extraction technique to achieve this result. One good feature of our construction is our scheme support multi-bit plaintext. Although Ananth, Karaoglu, and Liu presented one-time single decryptor encryption without any assumptions, but this only supports a single bit plaintext. Note that we cannot use standard parallel repetition and hybrid argument in the unclonable setting. So we don't know how to expand the plaintext space in our setting. And we can construct our single key, succinct key ciphertext policy FE by using hash encryption and garbled circuit. These tools can be instantiated with the standard LW assumption. So we can achieve our construction by using LW assumption. How many minutes I have? No. Okay. Okay. So I don't have much time, so let me skip the construction. Please see the paper for the detail. And I want to say that we also achieved the copy protection for single bit point function and unclonable predicate encryption by using the unclonable encryption. This is a general construction. So if the underlying unclonable encryption satisfies the standard unclonable indistinguishability, the resulting construction also satisfies the standard unclonability. Okay, let me summarize my talk. We propose new definition for unclonable cryptography, and we also constructed one-time secret key multi-bit single decryptor encryption from the LW assumption. So we can obtain the one out of many unclonable indistinguishable encryption from the LW assumption. That's all. Thanks.
Any questions from the audience? I have a question. So do you know if we can construct one out of many curve prediction for other interesting class of functionalities like pseudonym functions and so on from assumptions weaker than IO? Because that is something that is still sort of open, right?
Yeah, yeah, I think so.
Okay, okay. Oh, yeah, okay.
So your construction of single decrypted encryption, like you said, we have also a construction of single decrypted encryption in the usual definition, not the one out of many definition.
Our single decryptor encryption is under the standard definition. not a one out of many definition.
So it doesn't follow from the schema you showed for the one out of many, right? Like the schema.
Are you saying that we get
Yeah, in this picture.
okay, yeah. No, so yeah, we can get one out of many unclonable encryption, but so here there is not ZZ20's SDE is different from CLZ21's SDE. So our SDE is under the definition by CLZ21.
Okay.
So this equivalence result doesn't hold for the CLZ21 definition. So we cannot go to the one unclonable encryption under this definition.
Sure, but I'm saying your single decrypted encryption construction, which is in the usual definition, that is not part of this schema at all, right? Or it's completely independent? Like you have here one out of many single decrypted encryption, right? But you also have a construction which is not one out of many, which is the usual thing, and that is completely different from this.
No. So not completely different because one time strong anti-piracy SDE implies one out of many SDE. So the construction is the same.
So this is
So,
your
yeah, we constructed this one. So we construct this one. So immediately imply one out of many SDE.
so this
construction
is
is
so
same.
this one time
Yeah.
one is the construction in the usual
one
definition.
time construction.
I see. Okay.
Thanks.
Yes, we don't have time for more questions. Let's thank the speaker again.
Thank you.
Okay, so the next talk is about how to achieve copy protection for non-trivial functions in the plain model and with classical communication. And Paul is going to give the talk.
Thanks. So hi everyone. I'm gonna talk about semi-quantum copy protection and more, and it is a joint work with Céline Chevalier and Hui Vu. Before talking about semi-quantum notion of copy protection, I will briefly recall what is copy protection. So it's a primitive in which you have a quantum vendor on the left that will pick a function f from a family of function and protects this function using a protection algorithm to get a quantum state that is a quantum protection of f. Then he will send this quantum protection to the client, and with this protection, the client will be able to evaluate this function on any input x. And roughly speaking, the security of this primitive says that any malicious client cannot split this quantum protection to get two quantum states that can be used both to compute to evaluate the function f. So in this setting, as I said, the vendor is quantum and he communicates with the client using quantum communication. And the semi-quantum copy protection is the setting in which the vendor is classical. And so he has to communicate with the clients using classical communications. And then what he has to do is to classically instruct the vendor on the client, sorry, on how to construct this quantum protection of f while preserving the security of this primitive. And so how to do this kind of a primitive? So first, I want to mention that in a lot of copy protection schemes in the literature, the quantum states that are used are coset states. So a coset state is can be seen like is this state here, and it can be seen as given a subspace A and two vectors n and s prime, the superposition over all the vectors in A plus S, and in some way also the superposition over all the vectors in A plus S prime, which I would call the dual coset. And from these quantum states, it's easy to get a vector in the regular coset by just measuring in the computational basis. And it's also easy to get a vector in the dual coset by measuring in the diagonal basis. But it's impossible to get a vector in both of these cosets. And this is due to the destructive properties of quantum states. And this property is called the direct product hardness. Well, actually, in order to build our copy prediction schemes, we will need something a bit stronger than that, which is called monogamy of entanglement. And so monogamy of entanglement is another property of coset states, and is captured through this game in which we have a challenger sending a quantum state to Alice, which will have to split this quantum state into two quantum states, sigma 1, sigma 2, that can be entangled. And then we'll have two other adversaries, Bob and Charlie. Each one of them will get a piece of a share of this quantum state, sigma 1 or sigma 2, and will be given also the description of A. And they will have to, for Bob, output a vector in the regular coset, and for Charlie, output a vector in the dual coset. And this has been proven by Kolf and Vidic to be impossible to win. But yeah, what is important is that for constructing our copy prediction schemes, we will ultimately need to reduce to this game. And because we want semi-quantum version of this scheme, we want a semi-quantum version of this monogamy of entanglement game, meaning that now the challenger will classically instruct Alice on how to construct a random coset state while preserving the hardness of this game. And this is actually the main contribution, the main technical contribution of our work, is how to construct such what we call a remote coset state preparation between a challenger and Alice here. So I will give a quick overview of on how we construct this protocol. So we'll combine two protocols, one which is a quantum FHE based coset state preparation, which is very similar to what we want to have, but the one we will use have a weaker security than what we want to get. And in order to overcome this weaker security, we will combine it to a so-called self-testing protocol of BB8 for states. I will give a bit more details on what is self-testing later. But the idea is that the protocol that we use for BB8 is for BB8 for states, which are simple states. And we want to have the same kind of protocol that for coset states. So we'll combine these two protocols and get this self-testing of coset state protocol. But this is not completely over, because we want to have, like in the self-testing, we don't have any state in the end. So we want to have, we will need to slightly modify this protocol to get a remote coset state preparation, which is what we want to have ultimately. So first I will describe this pure quantum FHE based coset state preparation by Schmeli in 2022. So it's based on quantum FHE, and yeah, a bit of notation before. So whenever I write X or anything else on a yellow square, it means that it's encryption of X using 2FHE. And so quantum FHE works in the following way. So in order to evaluate an encryption of X on a circuit C, you will get two parts. So quantum part on the left and the classical part on the right. And the quantum part will be this QOTP C of X. So C of X, because C is a quantum circuit, will be a quantum state. And QOTP is quantum one-time pad, is just masking this quantum state with a key SS prime. And the classical part will be the encryption of this SS prime. So now how this preparation protocol works. So we have a sender and a receiver. The sender will send an encryption of a subspace description A to the receiver. Then the receiver will evaluate this encryption on a circuit C, such that C on A outputs the superposition over all the vectors in the subspace A. And this is called a subspace state. And what this receiver will get out of this separation protocol is actually the quantum one-time pad masking of this subspace state, which is actually exactly a coset state. So it will get this coset state A, SS prime. It will also get the encryption of the key S and S prime that it can send back to the sender. And the sender, because it has the key, will be able to decrypt everything, gets the description of the coset state, while the receiver has the coset state. But the problem of this protocol is that in our case, in our monogamy of entanglement setting, there is a simple attack, a simple cloning attack. And mainly it's due to the fact that we do not check whether the receiver really compute the right circuit during the evaluation class. And so the solution is to use, as I said, a self-testing protocol with this combined with this quantum fully homomorphic encryption-based process separation protocol. And so we will use a self-testing protocol of BB8 equal states presented by GMP 22. And so this self-testing protocol works in the following way. So we have a verifier interacting with the prover, and the idea is that the prover will first sample some, prepare some plus states, then commit to the plus state using some kind of Mahadev commitment for those who, for those who know what it is. Then they will continue to interact. And what is important here is that right before the final message from the prover to the verifier, we know that first the verifier will know some theta v, which is a description of a BB84 states, and the prover has in its memory the corresponding BB84 states. And that is true even for a malicious prover. That is true even for a malicious prover if the verifier accepts in the end of the protocol. So we'll just make a couple of observations here on how we can modify this protocol. So the first one is that we can change the way the prover prepares these plus states. And this is done by the verifier sending an encryption of 0 to the prover, and the prover evaluating this encryption of a circuit C, which on 0 outputs these plus states. So actually what we will get is not exactly these plus states because it will be masked by the quantum one-time pad, but it will be close enough and it's sufficient to show that with this new preparation, we can have the same correctness and the same soundness. So this protocol is exactly the same in terms of correctness and soundness than the previous one. And because we use quantum FHE, we can combine it. We can actually change the encryption. And instead of sending the encryption of 0, we can send the encryption of A. And the prover will evaluate on the same circuit as we saw before. And so you will get a coset state. And by changing some things, by doing some intent change on the verifier part, we can show that this actually, the verifier will get the description of the coset, and the prover will get the coset in the end. And it will be completely indistinguishable from the previous protocol where we sent the encryption of 0. And because of this fact, we can combine these two protocols, so send a bunch of encryption of 0 at the beginning, then once we are sure that the prover is honest, send a round with the encryption of A, and it gives us actually in the end a self-testing protocol for the coset state. Okay, so I will skip the last part, but basically we just have to run this protocol. Once you have the self-testing, we just have to run it in a n among 2n credentials way to get the remote coset state preparation. And yeah, thank you for your attention.
Questions? I have a couple of questions. So one is that in GMP, they have this inverse polynomial error.
Yeah.
And do you incur that error or?
Yeah, actually, so we have this error in the end. So the state that the prover gets in the end is coset states up to some point in that error. The thing is that we don't need to check exactly that we don't need this prover to have this coset state exactly. We only need to say that if it doesn't have these coset states, as long as it cannot win the monogamy experiment, it's fine, and that we can show it with negligible.
Okay, I guess what you're saying is that you don't need that strong rigidity statement that they have.
We don't need a perfect soundness to get our secret.
One other quick question. So you talked about like replacing encryption of 0 with encryption of A. mean, I guess Alice cannot distinguish this, but later on, Bob and Charlie do receive A, right? Can't they actually distinguish?
Yeah, I see your points. But I guess that so they can't distinguish, otherwise they could break the
Yeah.
security. So I don't know how, I don't remember how we got rid of this problem, and we show that it's not a problem anymore.
Let's thank the speaker again. The next talk is about pseudorandom states with interesting properties and their cryptographic applications. It's by Amit Pera is going to give the talk.
Hi, can you hear me? All right. So thanks for having me. So today I'm going to talk about pseudo-random quantum states, proof of destruction. It's a joint work with Zvika Vekelski, Bushmeli, and Oshatat. Okay, let's get started. So let me start with the first part of the title, which is pseudo-random quantum states. We have already seen a few presentations discussing this. So let's recall what it is. So it's basically, again, like an efficient quantum algorithm, generator gen, along with the key space or the seed space, such that this algorithm gen, for every key in the key space, outputs a pure state psyche, or quantum state psyche. And the pseudo-randomness basically says that for any efficient adversary and any polynomial T, the following two scenarios are indistinguishable. In the first scenario, the challenger samples a key from the uniformly at random and gives few copies of psyche. And in the other case, the challenger samples just a hard random state. So hard random is like the analogous of uniformly random string in the classical setting. So in the quantum setting, we say like it's a continuous space, so it's a hard measure. So hard random state phi, and gives q copies of phi to the adversary. And by indistinguishability, you again mean the usual indistinguishability, that is the probability that the adversary outputs one is close in both settings, negligibly close. All right. So as you can see, this is just like a PRG, but with the only difference that we give many copies of the output state instead of one. This is because in the quantum setting, you cannot get many copies of the output state, output quantum state from one copy, because cloning is not allowed. And in fact, in pseudo-random states, it's computationally hard to clone. Okay. So now that we saw like an analog of PRG, the natural next step would be to see an analog of PRF. So this is what we call pseudo-random function-like states, or PRFS. So we have two acronyms now: PRS for pseudo-random states and PRFS for pseudo-random function-like states. So now we have an input space along with the key space and the generator algorithm, and so it's again the generator algorithm takes a key and an input X and outputs a pure state. And again, the pseudo-randomness condition we can view as the following: again, an indistinguishability game. But now in the first case, the adversary receives the following. So the challenger samples a key at random and gives oracle access to the gen with the key K hard coded in it. And the other setting, the adversary gets access to the hard oracle, where the hard oracle basically samples a hard random state mu x for every input x, and every time the adversary asks for queries x, it just outputs mu x. And again, the same indistinguishability as we saw in the previous slide. Okay. Now, let me go to the next part of the title, which was quantum states with proof of destruction. So I would like to illustrate this with the following example of quantum money. So imagine you have a bank which has some secret classical information K, and using which it mints money states sigma. And now a user, a customer, Bob, comes up and says, look, I have some money and I want to deposit it to an account. It could be his own account or somebody else's account, but he wants to deposit. So how can he accomplish this task? So one way is to just send this quantum state over a quantum channel, and then the bank can just verify, and if the verify using the secret key, and then if the verification passes, then the bank can top up the account. But in this way, the problem is that this quantum channel with which Bob sends the state could have noise, and they can be notoriously hard to deal with. So is there like a easier way to do this just by, let's say, sending classical bits? So this is where proof of destruction come in. So what Bob can do is that he can measure the state in some basis that is prescribed by the bank publicly. And this measurement is destructive in some sense. So it will destroy the state Bob possesses, and instead output this classical proof P, and then send this proof P to bank. So Bob sends the proof P to the bank, and the bank has a secret key using which the bank can verify. And if the verification passes, then the bank is assured that indeed Bob had this money state and he destroyed it now. So he can so the bank will deposit the money. Okay. Now that we have seen both these notions, let's see some of the previous works that tries to accomplish this. So there has been a lot of work that uses these co-state states that we just saw in the previous talk to achieve many cryptographic primitives that exploit this proof of destruction property. And so all of these constructions achieve proof of destruction, but these states, co-state states, have too much structure. So you can easily distinguish it from random. Hence, these are not pseudo-random. On the other hand, we have these constructions of pseudo-random states based on these random phases. So they do achieve pseudo-randomness by design, but unfortunately, for these constructions, we don't know like how can we achieve proof of destruction, essentially because of the same reason, that we don't have enough structure there to work with. So in this work, we managed to kind of meet in the middle, and by modifying this random phase state construction and achieve both pseudo-randomness and proof of destruction. Okay, now let's see formally how to combine these two notions. So let's look at the definitions. So this combined idea we call pseudo-random states, it's proof of destruction. So now it becomes PRSPD. My apologies for the long name. Okay, so what's the definition? So we have a key space again, and now, but we have a triplet of efficient algorithms, not just one. So the first one is again the generation algorithm that takes a seed K and outputs psi K. But now we also have the destruction algorithm that takes a quantum state and outputs a classical string. So you can think of it like a measurement. And then we have the verification algorithm that uses the secret key to verify the authenticity of an alleged proof P. And correctness basically said that if you have like if you generated a state using the gen algorithm using a key K and then use destruct on it, then the resulting proof will pass verification with respect to the key. So I hope the notion is clear. So okay, now let's look into the security of this definition. So first is pseudo-randomness. So again, for this part, you can just for pseudo-randomness, you can think of the PRS-PD family as just a PRS family, like a pseudo-random state family, and then demand pseudo-randomness. So that is exactly the same here. Next is unforgeability of proof, which was not there in pseudo-random states. And this can be explained in the following unforgeability game. So the adversary has access to the verification oracle. So think that the challenger sampled a key K and gave oracle access to the verification with respect to key K, and also gave T copies of the state psi K. Now this T is some polynomial that the adversary can choose, and then the adversary wins if he manages to produce T plus 1 distinct proofs that pass verification. And we say that this scheme achieves unforgeability of proofs if there is no QPT adversary that can do this except with negligible probability. All right. So now let's look into our construction. So as hinted earlier, our construction is based on modifying the random phase state construction for pseudo-random states. So it's a good idea to let's recall the PRS construction there. So So this construction uses pseudo-random function family or PRF, and the key space of the PRS family is the same as the key space of the PRF family, and the states basically look like this. For every key k, the psi k is basically a uniform superposition, but with this random phase determine this function fk. Okay. So what we managed to do is that, look, the previous the construction there has the problem that it's the superposition is over the whole, like all the strings, and therefore we don't know how can we do proof of destruction because there is not enough structure. So what we do is that we sparsify the construction. So we have the same construction, but instead of taking like superposition over all strings, we take superposition over a pseudo-random set of size 2 to the n by 2. Now you should interpret this size 2 to the n by 2 is something which is super polynomial. So it is enough to fool the distinguishing adversary in the pseudo-randomness game, but it is still asymptotically smaller than the whole space, so that we have enough structure to do proof of destruction. So how do we achieve this pseudo-random state is that we use a strong PRP. So our pseudo-random state is basically you take a random permutation from this family and you apply it on this fixed set of size 2 to the n by 2, which is, you can take any set, but we took this set, all set of strings with prefix 0 n by 2. And therefore, the key space now becomes the product of the key space of the PRF and the strong PRP. Just to remark, we need the strong PRP in order to construct the superposition because we also need the inverse access to the inverse permutation. And now the destruct algorithm is simply measuring it in the computational basis, and verification is just checking membership in this set SR, in the pseudo-random set SR. All right. So so we so far only talked about PRSPD or pseudo-random states with proof of destruction, but we can also associate proof of destruction with pseudo-random function. And then it turns out this definition can be naturally generalized, and also our construction can be naturally generalized. So what we actually get is that we can construct both PRSPD and PRFSPD from one-way functions. Now let's look into a few of the applications. So it was shown that pseudo-random states and pseudo-random function-like states has a lot of applications in quantum cryptography. So what we managed to show is that with proof of destruction, okay, so all these constructions use quantum communication, like the protocols and the primitives both use quantum communication. So what we managed to do is to get these with classical communication using proof of destruction. Okay, but why is this interesting? Well, it's interesting because as we saw earlier, that there is this separation result between PRS and PRFS from one-way functions. So what it also says is all these applications is also separated from one-way functions. But remember, these applications are with quantum communication. So so the question is, can we have a similar separation with classical communication as well? And do we have such a thing? The answer is we don't know yet, because the same separation that works for pseudo-random states and pseudo-random function-like states do not work for the proof of destruction analogs. And therefore, we still don't know if with classical communication, these protocols are weaker than one-way functions. And therefore, the main open question that remains is, can we show that both PRSPD and PRFSPD are weaker than one-way functions? Okay. And so if you look at the current status of microcrate, it looks quite complicated. And the point of it is just to show how like it has got complicated, and there are many open directions here that needs to be investigated. And with that, I would like to conclude.
Oh, one question.
I think if you use log qubit output PRSG, you can also realize some classical channel application. How this is different from?
Yeah, so we don't know so that's true. There's another route to get this classical communication using log output, logarithmic output pseudo-random states and pseudo-random function-like states. So yeah, these two assumptions, we don't know the relation between them yet, like which one is like, it might be the case even that both of them are incomparable, but currently we don't have any evidence to show that one is weaker than the other.
So PRSG can be broken with PP Oracle.
Yeah.
So can you break your primitive with QCMA Oracle?
It's not clear, but you might. The reason I'm saying it's not clear is because this proof of destruction, they are not really deterministic from the key. So there might be issues if you want to apply the same argument, but yeah, I don't know. I cannot say you cannot.
Any other questions? Okay, let's thank the speaker again. So the next talk is a soft merge of two talks. The first one will be presented by Julia Manavolta. The talk is on weakening assumptions for certified deletion.
Hello. Let me figure out this works. Okay. Great. So thanks for the introduction. I'm going to talk about weakening assumptions for publicly verifiable deletion. This is a joint work with James, Dakshita, Alex, and Michael. Okay, so let me start off with explaining what we're doing in the scenario that we consider. So we consider a scenario where a client holds some data and they want to outsource it to a server. And at some point, the client says, okay, please delete my data. And the server will send a certificate. At that point, supposedly the data is gone. So, okay. Now, if you consider classical information alone, is not hard to convince yourself that this task is only possible if the server is honest and tries to cooperate with you. Whereas when taking into account also quantum information, then we can hope to actually achieve this also in a setting where the server is malicious. And that's exactly what we're considering. But maybe a slightly nuanced point is that even using quantum information, we have to always keep in mind that there must be some information about the data which is not known to the server. And one way to enforce that, otherwise it's clearly impossible. So one way to enforce that is to consider a server which is computationally bounded, which is QPT. And this motivates us and other people to look into many cryptographic primitives with certified deletion. So you can define certified deletion for primitives such as commitments, secret key encryption, public key encryption, and so on and so on. And those are all well defined, and you can try to construct. And that's essentially what we're trying to do in this work. Now, before telling you what our results are, let me show you what's known. This is a very active area of research, and here is an incomplete list of paper that consider this problem in one setting or another. But one thing that all these works have in common is the fact that the deletion process as privately verifiable, a private verification algorithm, which means that to verify that the data has been effectively deleted, you need some secret information that should not be revealed to the server who is supposedly deleting it. Now, here are a few works that actually consider the problem of public verification for deletion, in the sense that there is no secret information needed to verify the deletion. Here, a work of Bartusek et al. Consider this problem in the context of obfuscation with certified deletion. And a follow-up work by James, Dakshita, and Alex show a general compiler for publicly verifiable deletion, which, in addition to the security of the primitive that you're considering, it also requires to assume the existence of almost regular one-way function. It's not maybe super important to know what this object is, but it's somewhat a more structured version of one-way function. And our main result is to directly improve on this work and show a general compiler for certified deletion, assuming just one-way function. So any one-way function, and but we also have, as an additional result, we also have a generic compiler using a one-way state generators. Although in this setting, we obtained a scheme where the key to verify deletion is a quantum state. Okay, and so of course, the difference between these two settings is that the assumption of one-way state generators is believed to be a weaker assumption than functions. And I also want to mention the existence of a concurrent work, which you will hear next, where they present a compiler which is very similar, but somewhat interesting is not identical, and also assumes one-way function. And they also have a very beautiful argument to show that this compiler is somewhat uses in a sense minimal assumptions. Okay, I'm not going to say more because we're going to hear the talk of Takashi next. Good. So without further ado, I will show you our compiler for the simplified setting of one-way functions and considering just an encryption scheme, which I think is sufficient to convey the intuition. And the compiler is very natural. So the verification key simply consists of two images of a one-way function. And the ciphertext consists of an encryption of x0, x0, x1, along with the following quantum state, which is just a uniform superposition of x0 and x1, which are the preimages of y0 and y1, except that we sort of conditionally flip the phase, depending on whether we want to encrypt the 0, 1. So now you should think of the message here as the bit. It's a very natural compiler. So I have to tell you two things: how to decrypt and how to delete. Okay, so if we have the secret key, decryption is very easy. You can just measure the state in the Hadamard basis, and with the result of the measurement and along with the secret key of the encryption, you can actually recover the message. So exercise for you to figure out how to do it. Very simple. Whereas for deleting, of course, what do we do? Well, we just measure in the conjugate basis. So we measure in the computational basis. And if you look at the state, what you will get just one of the two preimages with equal probability. And at this point, it's obvious how to verify. You can just simply check whether whatever you get is either a preimage of y0 or a preimage of y1. So very natural. Now the main theory. Sorry, yes. Forgot to say that this actually is a technique which was inspired from recent work of quantum public key, one of which you heard earlier in the session. Good. So the main theorem that we prove here is this one. So we consider two experiments. The experiments are identical in the sense that we could just give the adversary all the information that was said before. The adversary returns a string x0, which is either a preimage of y0 or y1. And the only difference is the phase of the state. So the relative phase of the state, which again models precisely having an encryption of 0 or an encryption of 1. And in this context, we want that if we consider the joint distribution of the state of the adversary, the trace distance between these two experiments is negligible in lambda, and lambda is a security parameter. And for those of you who don't know what the trace distance is, that's essentially the sort of quantum analog of the L1 norm that we normally see for distance between probability distributions. Good. So it's a statistical property. Maybe that's the important part. Now, I claim that the proof is not as obvious as you might think. For instance, like a natural way to prove that these two distributions are indistinguishable would be to sort of switch the encryption to be an encryption, let's say, of 0. But that doesn't work precisely because the property that we want to show is a statistical property. So you're not allowed to change a distribution in a computational way, but not in a statistical. So that change is computationally indistinguishable, but statistically detectable. So would not be allowed. So we have to use a different strategy, which I'm going to outline next. So the first step of the proof is somewhat standard in this setting, which consists of sort of delaying the choice of the bit. So we sort of entangle the phase of the quantum state as you saw it before with an extra register that we keep locally, which contains a uniform superposition of 0. And in the second step, we instead of just measuring the register in the computational basis, we first measure it in the Hadamard basis and then measure it in the computational basis. And at this point, it's sort of obvious that the success probability of the experiment will be exactly 1/2, because we're guaranteed that the register, after we measure it in the Hadamard basis, is exactly, it's exactly at 45 degrees with the computational basis. So the probability that we'll get 0, 1 is exactly 1/2. Okay. So the way in which we actually use the property of the encryption scheme is by arguing that the view induced by the step 1 and step 2, they are computational distinction. So it's a little subtle, but somehow we have to use the fact that we have to be able to use the property of the encryption just to argue that these two experiments are computationally distinct. So we use it in a somewhat indirect way, but it works. Good. Okay, so with that being said, I'll wrap up and I'll give the stage to Takashi. So let me just quickly summarize. We presented a compiler, general compiler for certified deletion, for X being your favorite cryptographic primitive, commitments, PKE, ABE, FHE, and so on, assuming either one-way function or one-way state generators. And let me tell just very few open problems. An very interesting open problem is just to make this construction, for instance, practical, like that you can build using quantum hardware that we have today. For instance, you would be able to do it if you can construct this scheme using what I call product states, so like qubit by qubit states, which is not the case for our construction. For instance, like BB84 states are good states that we can prepare. Another interesting question is really if you can do it even from weaker assumptions, placing maybe a little bit more constraints on the setup, for instance, allowing quantum states for verification key. So it's in that case, it's not clear that this is an optimal approach. And of course, a very interesting open-ended question is whether you can do more cryptography with certified deletion. Part of the research question is to figure out what that even means. And okay, yeah, with that being said, I'll leave the stage discussion. Thank you.
Any quick questions to Julio? So you mentioned that the traces between out 0 and out 1 was negligible. Unless I misunderstood, aren't you considering orthogonal states? Isn't x0 plus x1 orthogonal to x0 minus x1? So how can the resistance be negligible there?
Sorry, let me go back.
Yeah, so
you mean, okay, good. No. Okay, so let me be more precise what I mean. So I mean that if I consider an experiment after the adversary has output some x star such that is either a preimage of x0 or x1, like the residual state.
Oh, I see.
Okay. In the sense, like this essentially means if the adversary was honest, he would have measured that state in the computational basis. So any information in the phase would have been erased.
Yeah, thanks.
More quick questions?
Okay, thanks. The next talk is by Takashi Yamakawa on publicly verifiable deletion from minimal assumptions.
Thank you for the introduction. So I will talk about this work. So this is our result. We construct a generic compiler that has the publicly verifiable deletion property for various kinds of encryption schemes, only using one function. And as Jerry mentioned, this conclusion is almost the same as their work, the previous talk, except for some minor difference. But I would like to mention that the constructions are not identical, and the idea is quite different. And our main idea is to generate signatures for BBH states. And this idea is inspired by a recent work on FE function encryption with certified deletion, which is our another work. And we also give some additional observation that the assumption can be weakened to a minimum one. And I remarked that one function may not be a minimal assumption in quantum crypto. And we observed that the one function in our construction can be replaced with what we call hard quantum planted problems for NP, which I will explain later. And because Jerry already gave background, so I will directly go into the technique. So before explaining our idea, let me first introduce the previous compiler for private verifiable deletion by Bartek and Grana. So this is notation. So for L-bit string X and theta, X sub theta means the BB84 state corresponding to X and theta. And ENC is an encryption algorithm of some encryption scheme that may not support touch-by deletion. And for encrypting the one-bit method, MSG, the encryptor first uniformly samples L-bit strings X and theta, and the ciphertext is described like this. The first component of the ciphertext is encryption of the basic choice theta, and the message masked by the XOR of OR XJ corresponding to the Hadamard-based position. And the second component of the ciphertext is the BB84 state corresponding to X and theta. And for decryption, if one is given the decryption key for ENC, one can first recover the base choice theta, and then by using the BB84 state, you can recover X, and finally you can unmask the message. I mean the mask part of the message to recover the message. And for deletion, the receiver measures the BB84 state in the standard basis and simply sends the measurement outcome as a deletion certificate. Then the verifier checks if this deletion certificate is consistent to the original X or the J in the standard basis positions. And intuitively, for passing this verification, the receiver has to measure the BB84 state in the standard basis. But after such a measurement, all information about X in the Hadamard basis position disappear. And after that, the other battery, I mean, the receiver cannot recover the message, even if it is given the decryption key. And so this is a nice compiler, but the caveat of this construction is that it is only privately verifiable. Why? This is because the verifier has to know X and theta for checking this. But X and theta should be kept from the other battery, kept secret from the other battery, and this is only privately verifiable. So our idea is to generate a signature for X theta, I mean BB84 state, so that the verification can be done by a public verification of the signature. And but signing on the quantum state is in general known to be impossible. But our key observation is that in their compiler, the verifier only needs to verify the consistency in the standard basis position. So we can simply run a signing algorithm of some signature scheme in superposition like this. So basically, for state 0, we generate state 0, sigma 0, and 1, force 1. This is mapped to 1, sigma 1, where sigma 0 and sigma 1 are signatures for messages 0 and 1, respectively. And for Hadamard-based states, we simply do like this. And for Hadamard-based states, this signature doesn't ensure anything about the state, but for standard-based bits, this does certify the bit. And this is enough for our construction. And as notation, we write U sig K to mean the operator that applies this map for each qubit by using the signing key sig K. And then our construction is described like this. So this is very similar to the BK construction, except for the following differences. The first, we also encrypt the signing key by using ENC. And the second, we apply this operation using K to the BB84 state. And for deletion, similar to the BK construction, we simply measure this state in the standard basis and send the measurement outcome as a deletion certificate. And the measurement outcome now looks like this. So the pair of the bit and its corresponding signature. And the verifier now only checks that the all message signature pairs are valid. And I remark that this is publicly verifiable because the signatures can be publicly verifiable. And also, we can reduce the certified deletion security of this construction to that of the original BK construction, because as I already explained, the signature certifies the bits on all standard basis positions, and so we can simply reduce. By using this, we can there is a straightforward reduction to the original one. And next, I will explain what signature schemes to use to instantiate our construction. And in our construction, we only generate one signature per signing key. And so we can simply use one-time signature. In particular, we can use Lamport signature based on any volume function like this. And moreover, we observe that we can actually use something weaker assumption, which we call hard content planted firm of NP. But what is this? So this is specified by some content polytime sampler that samples the instance witness pair XW in such a way that any QPT out of 3 given only instance cannot find its witness. Then we can think of the instance and witness of this as a output and input of the boundary function. And by using the similar construction to Lamport signature, or we can construct similar one-time signature scheme. And we can use this signature scheme to instantiate our construction. And we also observe that this is the minimum assumption as long as the verification is classical. Why? This is because any publicly verifiable deletion encryption scheme with classical verification naturally implies this. Because the verification of the certificate can be seen as the NP verification algorithm. And so this is the minimum assumption in this sense. And this is a summary. Thank you for your attention.
Any questions for Takashi? Yeah.
So how does this assumption about the planted NP relate to other cryptographic primitives in microcrypt like EFI and let's say one-way generators? Because you said it's equivalent to this public verification, right?
So I don't know any other relationship between this assumption. I mean, for example, it's easy to see that this is, of course, weaker than the existing boundary function. And we can also say that the publicly verifiable deletion with the classical verification implies. And so by minimum assumption, I mean, for constructing this, we have to at least assume this. And this is why I said this is minimum assumption. But for the relationship between something else like the one-way SG or API, I have no idea, but I guess it's unlikely that there is any relationship.
Because this assumption of hard quantum planted problem for NP, won't it be broken by strong enough oracles? I think EFI is usually resistant to such attacks.
Yes, I mean, so far we don't know how to break EFI by using any classical oracle, but I guess for this we can break. So in that case, this cannot be reduced to EFI, and we can read. So, but there is no rigorous proof that EFI cannot be reduced to classical complexity. So I don't know. So if we can formally prove that.
Okay, thanks.
I have a question. So you said that this is a minimal assumption. So I can think of the certificate that you send back to be the witness. But what would be the instance here?
The instance is okay. So I haven't defined the syntax of the publicly verifiable deletion, but there is a verification key, and the verification key.
Oh, there's the
is
instance. I see. Any other questions? Okay, so let's thank all the speakers. Let's thank Takashi and also all the speakers of the session. Please don't go anywhere. Tal Malkin has a very, very important announcement.